In the rust-colored silence of Mars, beneath skies that glow pink with suspended dust, there lies a collection of dangers so subtle, so quietly devastating, that humanity's dream of walking on the red planet may be far more perilous than we have ever dared to imagine. For decades, we have gazed at Mars through telescopes and cameras, seeing a barren world, yes, but one that seemed almost familiar. A desert planet, a cold frontier, a place where human ingenuity might one day plant flags and footprints. Yet recent discoveries, emerging from laboratories and rover data streams across Earth, have begun to paint a very different picture. Mars is not simply inhospitable, it is actively hostile in ways that operate beneath perception, beyond our evolutionary preparation, and outside the boundaries of anything life on Earth has had to survive. Tonight, we journey not across distance, but across revelation. We will explore the hidden architecture of danger that makes Mars perhaps the most deceptively lethal destination humanity has ever seriously considered colonizing. The threats are not what science fiction taught us. There are no alien predators, no ancient machines buried in the sand. Instead, Mars kills quietly, microscopically, chemically, psychologically, through mechanisms so deeply woven into the planet's nature that simply being there becomes a form of slow siege against the human body and mind. The public imagination has long held Mars as humanity's next home, our backup planet, the red frontier where pioneers will forge a new chapter of civilization. Popular media shows us domed cities, thriving colonies, terraformed landscapes blooming with Earth life. This vision is beautiful, it is inspiring, it may also be dangerously incomplete, because while engineers solve the obvious problems, gravity wells and rocket equations, atmospheric composition and radiation shielding, scientists in specialized fields have been uncovering threats that don't make headlines, but may prove far more difficult to overcome. Threats that exist at the boundary between physics and biology, between planetary science and human physiology. What makes Mars uniquely treacherous is not any single danger, but the convergence of multiple hazards, each amplifying the others, creating a web of peril that surrounds any human presence like an invisible storm. The dust that coats everything is not merely abrasive, it is chemically reactive and microscopically sharp. The radiation that bathes the surface is not just intense, it is precisely the type that damages DNA most efficiently. The thin atmosphere is not simply too sparse to breathe. It creates pressure differentials that affect human tissue in unexpected ways. Even the soil, that rusty regolith that covers the planet, contains compounds that are toxic to Earth life at the molecular level. If you are watching this as you settle in for the evening, wherever you are on Earth, beneath skies that hold breathable air and magnetic protection, take a moment to comment below. Tell us where you are watching from and what time it is in your corner of the world. As we explore the hidden dangers of Mars together, it reminds us how precious and rare our own planet truly is. Now, let us descend gently into the details. Let us examine what recent research has revealed about the red planet's quiet hostility, and why the greatest dangers may be the ones we cannot see. When we imagine the dangers of Mars, we often picture dramatic moments, explosive decompression, catastrophic equipment failure, perhaps a swift and sudden end. Yet one of the most insidious threats on the red planet arrives not with violence, but with silence. It drifts on invisible currents. It settles on every surface. It penetrates every seal. Martian dust is not merely an inconvenience to be brushed away. It is, at the microscopic level, a relentless killer that operates on timescales measured not in moments, but in breaths. To understand this threat, we must first journey into the realm of the infinitesimally small. Under a microscope, Earth dust appears relatively benign, rounded grains smoothed by wind and water over millions of years, tumbled in rivers, worn down by rain, shaped by the patient hand of erosion. Martian dust is something altogether different. Mars has no liquid water to soften its edges, no thick atmosphere to cushion collisions between particles. Instead, Martian dust grains are angular, blade-like structures of silicate minerals, each particle a microscopic shard of volcanic glass, with edges that remain razor-sharp across geological time. These particles average just 3 micrometers in diameter, approximately 1/30th the width of a human hair, small enough to bypass many filtration systems, small enough to penetrate deep into lung tissue if inhaled. The composition itself tells a story of a world frozen in ancient violence. Iron oxide that gives Mars its crimson hue, olivine crystals formed in volcanic fire, and jagged fragments of basalt that have never known the smoothing touch of flowing water. On Earth, dust settles. On Mars, dust waits. But the mechanical danger of sharp-edged particles is only the beginning. Laboratory analysis of Martian soil samples, studied through rovers and analysed in simulations here on Earth, reveals something far more troubling: perchlorates. These chlorine compounds exist in Martian soil at concentrations between 0.5 and 1%, a seemingly small amount until we consider the implications for human biology. Perchlorates interfere with thyroid function by blocking iodine absorption, a process critical for hormone regulation, metabolism, and neurological development. Chronic exposure, even at low levels, can lead to thyroid disorders, cognitive impairment, and developmental problems. For any children born on Mars, the presence of perchlorates in the environment could pose existential challenges to normal growth. Yet even if we could filter every particle, even if we could seal every habitat perfectly, Martian dust possesses a property that makes it uniquely persistent: electrostatic adhesion. The thin Martian atmosphere and constant bombardment by solar radiation create conditions where dust particles accumulate significant electrical charges. Unlike Earth dust, which eventually falls and stays fallen, Martian dust clings. It adheres to spacesuits with stubborn tenacity. It coats solar panels, reducing power generation efficiency by up to 90% over time. It finds its way into mechanical joints, into airlocks, into the finest crevices of equipment designed with precision tolerances. Astronauts returning from surface excursions would carry this electrostatically charged dust with them, an invisible contamination that refuses to be brushed away. In the confined space of a habitat, this dust would gradually accumulate. Each sortie outside would introduce more. Each cycle of the airlock would draw particles inward. The dust would float in the recycled air. It would settle on food preparation surfaces. It would work its way into fabrics, into filters, into lungs. Long-term exposure simulations conducted in terrestrial laboratories offer a glimpse of what prolonged contact might mean. When human lung tissue cells are exposed to simulated Martian dust in controlled environments, the results are sobering. The sharp-edged particles cause mechanical damage at the cellular level, creating microscopic lacerations in delicate alveolar tissue. The body's immune response to these foreign particles triggers inflammation, a process that, when chronic, leads to conditions resembling silicosis or coal workers' pneumoconiosis. Over months or years, lung capacity would diminish. Breathing would become laboured. The simple act of drawing breath, would gradually become a struggle against an invisible enemy that accumulates with each passing day. And the dust is everywhere. Mars experiences dust devils, towering vortices that spiral across the surface, some reaching heights of 8 kilometers, far taller than any tornado on Earth. These whirling columns lift dust high into the thin atmosphere, where it can remain suspended for months, gradually settling in a perpetual rain of microscopic blades. The atmospheric circulation patterns on Mars create global dust storms that can envelop the entire planet. Events that last for weeks or even months, turning day into twilight and coating everything in a thick blanket of electrostatically charged particles. During the global dust storm of 2018, NASA's Opportunity rover, which had survived 14 Martian years, finally succumbed. Its solar panels, covered in dust, could no longer generate sufficient power. The rover entered a deep sleep from which it never awakened. If dust could kill a machine designed specifically for the Martian environment, what might it do to the far more delicate machinery of human biology? Current spacesuit technology, as advanced as it is, may prove inadequate for prolonged Martian operations. Suits designed for the Moon, where dust is also problematic but chemically inert, do not face the dual challenge of perchlorate contamination and extreme electrostatic adhesion. The seals on Martian suits would need to be perfect, not just good. The filtration systems would need to catch particles smaller than those they currently target. The decontamination protocols would need to be more thorough than anything yet devised, perhaps involving complete suit removal in specialized airlocks, where the outer layers never enter the main habitat at all. Some researchers propose magnetic cleaning systems, exploiting the fact that Martian dust contains iron compounds. Others suggest electrostatic repulsion fields or specialized coatings that prevent adhesion. Yet each solution adds complexity, adds weight, adds potential points of failure to systems that must function flawlessly in an environment where a single breach could mean catastrophe. The invisible nature of this threat makes it psychologically difficult to address. We are evolutionarily programmed to respond to visible dangers. The predator in the shadows, the cliff edge, the approaching storm. But dust is mundane. Dust is familiar. Our instincts do not warn us against something that seems so ordinary, so similar to the household dust we vacuum weekly on Earth. Yet Martian dust is not ordinary. It is an accumulation of microscopic weapons, each particle armed with chemical toxicity and mechanical sharpness, each breath drawing them deeper into the body, each day adding to a burden that the human organism was never designed to bear. To settle Mars is to accept that we will live in a state of perpetual vigilance against an enemy that measures 3 micrometers across, that weighs almost nothing, that seems harmless in isolation. But isolation is an illusion. There is no single particle. There are trillions upon trillions suspended in the thin air, waiting in the soil, clinging to every surface we touch. The invisible killer does not announce itself. It does not strike suddenly. It simply accumulates, particle by particle, breath by breath, until the damage can no longer be undone. In the story of Mars colonization, dust may not be the dramatic villain, but it is perhaps the most patient one. And on a world where patience is measured in geological time, that may be the most dangerous quality of all. Beyond the dust storms and barren landscapes lies something far more insidious, a danger that cannot be seen, cannot be felt, and cannot be escaped. Mars is bathed in radiation, not as a temporary threat, but as a constant presence, a silent sentence delivered the moment anyone sets foot on its rust-coloured surface. On Earth, we live beneath an invisible shield. our planet's magnetic field stretches thousands of miles into space, deflecting charged particles from the Sun and cosmic rays from distant galaxies. The atmosphere adds another layer of protection, absorbing and scattering radiation before it reaches the ground. Together, these defenses reduce our exposure to levels that allow life to flourish. But Mars has no such protection. Its magnetic field collapsed billions of years ago, a consequence of its cooling core. What remains is a planetary corpse, magnetically speaking, vulnerable to the full fury of the cosmos. The thin Martian atmosphere, less than 1% the density of Earth's, offers almost no resistance to incoming radiation. Standing on the surface of Mars is like standing on a mountaintop on Earth, except the mountaintop extends into the void of space itself. There is no shelter from above. Every moment spent on Mars means exposure to radiation levels that would be illegal in any occupation on Earth. Astronauts, nuclear workers, pilots flying at high altitudes, all are monitored carefully to ensure their cumulative exposure remains within safe limits. On Mars, those limits would be exceeded, not in years, but in months. Two primary sources of radiation dominate the Martian environment. The first is galactic cosmic rays, or GCRs, high-energy particles traveling near the speed of light, originating from supernova and other violent cosmic events far beyond our solar system. These particles are relentless. They arrive continuously, day and night, piercing through spacecraft hulls, habitat walls, and human tissue with equal ease. Unlike solar radiation, which fluctuates with the sun's activity, GCRs are a constant background hum of danger, impossible to avoid. The second source is solar particle events, sudden eruptions from the sun that release massive bursts of protons and heavy ions. These events are unpredictable and can occur with little warning. On Earth, our magnetic field channels these particles toward the poles, creating auroras, beautiful displays of light that signal the deflection of danger. On Mars, there are no auroras. The particles simply strike the surface, delivering doses of radiation that could be lethal within hours if astronauts are caught unprotected. Calculations of cumulative radiation exposure paint a sobering picture. A round-trip mission to Mars, including travel time and surface operations, could expose astronauts to radiation levels between 500 and 700 millisieverts. To put this in perspective, the average person on Earth receives about 2 to 3 millisieverts per year from natural background radiation. A full-body CT scan delivers around 10 millisieverts. The radiation exposure from a Mars mission would be equivalent to receiving a CT scan every few weeks for 3 years. Current safety guidelines for astronauts set a career limit designed to keep cancer risk below 3%. A single Mars mission could consume most or all of that allowable exposure. But the danger is not merely statistical. Radiation does not simply increase the likelihood of disease. It attacks the very foundation of life itself. At the cellular level, high-energy particles tear through DNA, breaking the delicate strands that carry genetic information. Some damage can be repaired by the body's natural mechanisms, but not all. Errors accumulate. Mutations arise. Over time, these mutations increase the risk of cancer, particularly leukemia, lung cancer, and cancers of the digestive system. The longer the exposure, the higher the risk. A Mars colonist living on the surface for years might face cancer risks that approach or exceed 20%, a level considered unacceptable by any terrestrial standard. Yet cancer is not the only concern. Recent studies have revealed something more immediate and more troubling. Radiation does not wait years to cause harm. it begins altering the brain almost immediately. Experiments with mice exposed to radiation levels similar to those found in deep space have shown measurable cognitive impairment. Memory declines. Decision-making becomes impaired. The ability to learn new information diminishes. The mice exhibit signs of anxiety and confusion, behaviors that, in humans, could compromise mission success and survival. If radiation affects the brain during the journey to Mars, astronauts may arrive not at full capacity, but already diminished, less capable of handling the extreme challenges that await them. The mechanisms behind this cognitive damage are still being studied, but evidence suggests that radiation disrupts neural connections, inflames brain tissue, and accelerates the aging of neurons. In essence, spending months in transit to Mars may age the brain by years. The implications are profound. A crew that embarks on a mission sharp, focused, and mentally prepared may arrive on Mars slower, forgetful, and emotionally unstable. The invisible sentence of radiation is not just physical. It is mental, psychological, existential. Efforts to shield against radiation have yielded mixed results. Traditional shielding, such as thick layers of metal or water, can reduce exposure, but only marginally. Adding enough shielding to match Earth's protection would make spacecraft prohibitively heavy, requiring fuel loads that current technology cannot support. Some researchers have explored the use of hydrogen-rich materials, like polyethylene or even human waste, to absorb radiation. Others propose constructing habitats beneath the Martian surface, using the planet's own regolith as a shield. But even underground, radiation penetrates. Secondary particles, created when cosmic rays collide with the Martian soil, scatter in all directions, creating a cascade of exposure that is difficult to escape. There is also the controversial theory of radiation hormesis, the idea that low levels of radiation might actually stimulate the body's repair mechanisms, making organisms more resilient over time. Some scientists point to populations living in high radiation environments on Earth, such as certain regions of Iran and India, where cancer rates do not appear significantly elevated. Could the human body adapt to Martian radiation? Could exposure, rather than being purely harmful, trigger protective responses that make long-term habitation feasible? The theory is speculative, not widely accepted, and experiments have produced conflicting results, yet it persists as a glimmer of possibility, a hope that biology might find a way where technology has faltered. What is certain is that radiation on Mars is not an occasional hazard. It is a permanent condition. Every sunrise on Mars brings with it an invisible bombardment. Every day spent on the surface is a day of accumulating damage. Unlike other dangers, which might be managed with technology or caution, radiation is ever present, unforgiving, and indifferent to human ambition. It does not discriminate, it does not pause, it simply continues, second by second, particle by particle, rewriting the fate of anyone who dares to stand beneath the pale Martian sky. To journey to Mars is to accept a sentence written in invisible ink, a sentence that may not be read until years later, when cells begin to fail, when memories fade, when the cost of reaching another world is finally tallied, not in dollars or kilometers, but in the years stolen from those who dared to go. Radiation is the silent sentence, and Mars is the courtroom where it is delivered without mercy. When we imagine Mars, we often think of red deserts and distant horizons stretching beneath a butterscotch sky. But the atmosphere itself, that invisible envelope that wraps the planet, is where one of Mars's most insidious dangers lies hidden. It is a paradox written in the language of physics, an atmosphere so thin it might as well not exist, yet thick enough to kill you in ways both immediate and slow. Too tenuous to breathe, too present to ignore. Mars's atmospheric pressure sits at approximately 1% of Earth's. To put this in perspective, standing on the Martian surface is equivalent to standing at an altitude of about 100,000 feet above Earth, 3 times higher than commercial aircraft fly, in a region where the sky begins to fade into the black of space. At this pressure, the rules of survival change completely. Water cannot exist as a liquid. It either freezes solid or boils away instantly, depending on the temperature. And the human body evolved for the thick, protective blanket of Earth's atmosphere, begins to fail in ways that are both rapid and terrifying. This threshold has a name, the Armstrong limit. Named after aerospace physician Harry Armstrong, it marks the altitude where atmospheric pressure drops so low that the boiling point of water falls below human body temperature, 37 degrees Celsius. Cross this limit without protection, and the water in your tissues begins to vaporize. Not all at once, not explosively, but steadily, inexorably. Your blood does not boil. Contrary to science fiction imagery, the circulatory system maintains enough internal pressure to prevent that. But the saliva on your tongue evaporates within seconds. The moisture in your lungs turns to vapor. Your soft tissues begin to swell as dissolved gases come out of solution, a condition called ebulism, where the body inflates like a grotesque balloon. Mars exists far beyond the Armstrong limit. Step outside a habitat without a pressure suit, and you have perhaps 15 seconds of useful consciousness before hypoxia, oxygen starvation, overwhelms your brain. Death would follow within 2 minutes, not from explosion, but from asphyxiation and the cascading failures of a body attempting to function in an environment it was never designed to endure. The Martian atmosphere is not merely hostile. It is incompatible with human physiology at the most fundamental level. And yet, paradoxically, this whisper-thin atmosphere is not empty. It is composed almost entirely of carbon dioxide, 95% by volume, with traces of nitrogen and argon. On Earth, carbon dioxide is present at just 0.04% of our atmosphere. On Mars, it is the atmosphere. This creates a secondary, more insidious danger for any enclosed habitat. Human beings exhale carbon dioxide with every breath. In a sealed Martian structure, this gas accumulates rapidly. Without sophisticated scrubbing systems constantly removing CO2 and replenishing oxygen, the air inside would become toxic within hours. Carbon dioxide toxicity is subtle at first. At concentrations around 1%, occupants might experience slight drowsiness. At 2 to 3%, headaches emerge, along with reduced cognitive function. By 5%, breathing becomes labored, decision-making impairs, and panic can set in. At 10% or higher, unconsciousness arrives within minutes, followed by death. The International Space Station maintains CO2 levels below 0.5%, a constant technological battle requiring redundant systems and continuous monitoring. On Mars, this battle would be perpetual, fought against an atmosphere that wants to seep into every habitat, every airlock, every sealed compartment, replacing precious oxygen with a gas that slowly suffocates. But perhaps the most haunting aspect of Mars's atmosphere is not its danger, but its beauty. Mars gives us blue sunsets. While Earth's thicker atmosphere scatters blue light during the day, creating our azure sky, and allows red wavelengths to dominate at sunset, Mars performs the opposite alchemy. Its thin atmosphere, laden with fine dust particles of a specific size, scatters red light throughout the day. painting the sky in shades of salmon and rust. But during sunset, when sunlight passes through a longer path of atmosphere near the horizon, blue wavelengths scatter forward, creating a soft, cool glow around the setting sun, a halo of cerulean light against a pink sky. This phenomenon is more than merely picturesque. It reveals the precise nature of Martian dust, particles approximately 1.5 microns in diameter, the perfect size to scatter red light preferentially. These same particles, suspended perpetually in the thin air, create another atmospheric danger: Martian dust storms. Unlike Earth's weather systems, driven primarily by water vapor and thermal convection from oceans, Mars generates storms through dramatic temperature differentials and the seasonal sublimation of carbon dioxide ice at the polar caps. During Martian spring and summer, frozen carbon dioxide at the poles vaporizes, temporarily increasing atmospheric pressure by as much as 25%. This additional gas drives winds that lift dust from the surface, sometimes creating storms that engulf entire hemispheres. The famous 2018 global dust storm that ended the Opportunity rover's mission darkened the sky so completely that solar panels could not generate power even at midday. These storms can last months, transforming the already thin atmosphere into an abrasive, light-blocking shroud that could trap settlers inside habitats for extended periods, unable to venture out, unable to maintain solar infrastructure, slowly depleting resources while waiting for the sky to clear. The challenge of creating Earth-like pressure within Martian habitats is an engineering feat that cannot be overstated. A habitat pressurized to Earth normal conditions, 101 kilopascals, exists under constant stress from the pressure differential. Every seam, every joint, every window represents a potential failure point where the precious atmosphere inside could escape into the near vacuum outside. The structure must be robust enough to resist this outward pressure continuously, day after day, year after year, without fatigue or degradation. Some mission planners have proposed reducing internal pressure to perhaps 30 to 50% of Earth normal, enough to keep humans functional while reducing structural stress. But this creates its own complications. Lower pressure environments require higher oxygen concentrations to maintain breathability, which increases fire risk dramatically. The Apollo 1 tragedy, where 3 astronauts died in a flash fire within their pure oxygen, low-pressure capsule, stands as a grim reminder of this balance between pressure, oxygen, and safety. Mars forces us to recognize that atmosphere is not simply air. It is a system, a delicate equilibrium of pressure, composition, and dynamics that sustains life through mechanisms we often take for granted. On Earth, we breathe without thought. On Mars, every breath must be engineered, filtered, pressurized, and carefully managed. The atmosphere there is simultaneously too thin to provide what we need, and too present to be dismissed as mere emptiness. As future settlers stand inside their habitats, watching blue sunsets through reinforced windows, they will live perpetually on the edge of this paradox, separated from death by walls of composite material and the humming of machines that work ceaselessly to maintain the illusion that the air around them is breathable, stable, safe. The Martian atmosphere will always be there, pressing inward with its carbon dioxide, waiting with the patience of geological time for any failure, any breach, any moment when human vigilance falters. It is beautiful, it is deadly, and it is perhaps the most honest representation of Mars itself, a world of contrasts where wonder and danger occupy the same space, inseparable and eternal. Beneath the rust-colored dust of Mars lies a silent chemical conspiracy, one that was not written by intent, but by ancient planetary chemistry. As we imagine the first human habitats on the red planet, we must confront a danger that cannot be seen with the naked eye, cannot be felt until damage is already done, and permeates the very ground upon which future colonists would walk. This is the threat of perchlorates, compounds so common on Mars that they may transform the dream of a self-sustaining colony into a medical nightmare played out in slow motion. The discovery came not with fanfare, but with curiosity. In 2008, NASA's Phoenix lander descended into the northern polar regions of Mars, extended its robotic arm, and scooped samples of Martian soil for analysis. What it found would fundamentally alter our understanding of Mars's habitability. Perchlorates, chemical compounds containing chlorine and oxygen, were present in concentrations far higher than anyone had anticipated, roughly 0.5% by weight in some samples. This may sound insignificant, a mere fraction of the soil's composition, but in the context of human biology, these numbers become profoundly troubling. Perchlorates are not strangers to Earth. They occur naturally in arid environments and are manufactured for use in rocket fuel, fireworks, and explosives. We understand their toxicity well. When absorbed into the human body, perchlorates interfere with iodine uptake in the thyroid gland, the small butterfly-shaped organ in our necks that regulates metabolism, growth, and development. The thyroid requires iodine to produce hormones that control nearly every cell in the body. Perchlorates, chemically similar to iodine, block its absorption. The result is hypothyroidism, a condition where the body's metabolic engine begins to slow, sometimes catastrophically. On Earth, perchlorate exposure is regulated, monitored, and controlled. On Mars, it is everywhere. Subsequent missions, including the Curiosity and Perseverance rovers, have confirmed that perchlorates are not isolated to Phoenix's landing site, but appear to be distributed globally across the Martian surface. They exist in the regolith, the fine, powdery soil that covers the planet. They exist in the dust that swirls through the thin atmosphere during global dust storms. They may exist in the subsurface ice deposits that future colonists would mine for water. Mars, it seems, is soaked in a compound that attacks one of the most fundamental regulatory systems in human physiology. Imagine a habitat on Mars, sealed against the hostile environment, recycling air and water in closed-loop life support systems. Astronauts venture outside in pressurized suits, their boots pressing into perchlorate-laden soil. Dust clings to their suits with electrostatic force, impossibly fine particles that resist simple brushing. They return to the airlock, removing their suits carefully, but dust remains. It settles on surfaces, floats in the recycled air, contaminates the water extracted from Martian ice. Every breath, every meal, every sip of water becomes a potential exposure event. The contamination scenarios multiply like a branching tree of consequences. Food grown in Martian soil, even treated soil, may absorb perchlorates through root systems. Hydroponic systems using water extracted from Martian ice could concentrate these compounds. Air filtration systems, no matter how sophisticated, must contend with particles measured in microns. Dust so fine it behaves almost like a gas. In the closed environment of a Mars base, perchlorates introduced into life support systems would not disperse into an infinite atmosphere as they might on Earth. Instead, they would circulate, accumulate, and potentially biomagnify through the very systems designed to sustain life. Biomagnification is a subtle horror. It occurs when contaminants become more concentrated as they move through recycling systems or food chains. On Mars, where every drop of water must be purified and reused, where waste must be processed and reclaimed. Perchlorates could accumulate in unexpected reservoirs. The lettuce grown in the greenhouse, the water reclaimed from humidity in the air, even the bodies of the astronauts themselves, all become potential concentrators of this thyroid-disrupting compound. What begins as 0.5% in the soil could become far more significant in the biological systems of a closed habitat. The implications extend backward through history as well. The Viking landers of 1976 carried experiments designed to detect signs of microbial life in Martian soil. They found puzzling results, chemical reactions that some scientists interpreted as biological activity, while others attributed to unknown chemical processes. Decades later, with the discovery of perchlorates, some researchers have proposed that these highly reactive compounds may have destroyed organic molecules in Vikings' heating experiments, potentially masking evidence of past or present life. The same chemistry that threatens human health may have concealed Mars's biological secrets, if such secrets exist at all. Yet the story of perchlorates is not solely one of danger. It is also a story of chemistry, adaptation, and potential solutions. Some researchers have explored biological remediation, bacteria that consume perchlorates and break them down into harmless chloride and oxygen. These microorganisms exist on Earth, thriving in perchlorate-contaminated environments. Could they be adapted to Martian conditions, engineered to cleanse water and soil before use? The idea is tantalizing, but raises profound questions about introducing Earth life to Mars, even microscopic life designed for our benefit. Physical and chemical methods offer alternative approaches. Water treatment systems using ion exchange resins can remove perchlorates, though such systems add weight, complexity, and points of potential failure to already intricate life support architectures. Soil processing might involve washing regolith before use in agriculture, but this requires enormous quantities of water, the very resource Mars offers so sparingly. Every solution presents trade-offs, each method balancing safety against resource consumption, simplicity against effectiveness. Some scientists have even suggested that perchlorates, despite their toxicity, could serve a purpose. Their presence lowers the freezing point of water, potentially allowing liquid brines to exist near the Martian surface, even in extreme cold. These same compounds, with their oxygen-rich structure, could theoretically be converted into rocket fuel and breathable oxygen through chemical processing. Mars offers a poison that might also be a resource, a duality that characterizes so much of the red planet's relationship with human ambition. As we contemplate boots on Martian soil, the perchlorate question becomes not whether exposure will occur, but how much, how often, and with what consequences. Thyroid function can be monitored, hormone supplementation provided, exposure minimized through careful protocols. But the fundamental challenge remains. Mars is saturated with a compound that interferes with human metabolism at the molecular level. Every grain of Martian dust carries this chemical conspiracy, written not by malevolence, but by billions of years of planetary chemistry, unfolding in an atmosphere rich in chlorine compounds and oxidizing radiation. The red planet does not merely challenge us with cold, radiation, or distance. It challenges us with its very composition, asking whether we can live on a world whose dust is fundamentally incompatible with the delicate hormonal systems that regulate our bodies. This is not a problem to be solved with engineering alone, but with biology, medicine, and perhaps a fundamental rethinking of what it means to sustain human life in an environment that offers survival only to those who can navigate its hidden chemical labyrinths. Long before Mars tests our technology, it will test something far more fragile, the human mind. the journey to the red planet is not only a voyage across space, but a slow, relentless crossing of psychological thresholds. On Earth, we have only glimpsed what this truly means through experiments, analog missions, and the scattered outposts we've built at the edge of our own world. We begin in Antarctica. Here, at the bottom of Earth, winter stations are cut off for months at a time. Outside, temperatures fall so low that exposed skin can freeze in seconds. Inside, a handful of people share the same rooms, the same corridors, the same faces. Day and night blur into endless darkness or unbroken light, depending on the season. Researchers in these stations report something subtle but profound. Time itself begins to feel distorted. Weeks stretch like years, but months vanish in memory. Small irritations become magnified. A misplaced tool, an offhand comment, the sound of someone's footsteps in the hallway. These tiny details can feel enormous in a sealed world. Mars will be Antarctica without the comfort of an exit sign. We already see early hints in Mars' analog habitats on Earth. Sealed modules in deserts, volcanic fields, and remote islands where crews live for months under strict simulation. They wear mock spacesuits outside. They follow delayed communication protocols with mission control. They cannot simply walk away. In these trials, participants report an emotional curve, excitement at the beginning, then a plateau of monotony, and finally a psychological descent into what some call the third quarter phenomenon, a stretch of time when the mission is well underway, but the end still feels impossibly far. Motivation dips, tension rises. The mind begins to push back against confinement. On Mars, that third quarter will not be a training scenario. It will be real life with no emergency evacuation flight, no quick return home. Just regolith, rust, and the same horizon every day. In orbit around Earth, astronauts can speak with mission control in near real time. A joke, a question, a worry, answers arrive in seconds. The illusion of closeness remains. Mars tears that illusion apart. At its nearest, Mars is still tens of millions of miles away. A signal from Earth can take around 5 to 20 minutes to arrive, depending on the alignment of the planets. A simple conversation becomes a staggered exchange across a gulf of time. Are you okay? 20 minutes of silence. Yes, just tired. What do you suggest? Another 20 minutes of silence. Support becomes asynchronous. Comfort is delayed. A cry for help, emotional or practical, cannot be met with instant reassurance. On Earth, we are used to typing a message and seeing 3 little dots appear. Proof that someone is there, listening, responding. On Mars, there are no 3 dots. Only a quiet screen, and the knowledge that even when the reply comes, Earth is not with you in the way it used to be. This time delay does more than stretch communication. It stretches identity. A Martian crew is forced to think and act as a fully autonomous society, even if that society is only 6 or 10 people. Hierarchies with Earth become softer, suggestions rather than commands. Responsibility thickens. Every choice feels heavier when you know there is no one who can step in quickly if you are wrong. Inside the habitat, the world shrinks further. Martian bases, especially in early missions, will be compact, controlled, and unforgiving of error. Air will be measured. Water will be accounted for. Every object has a purpose. There are no casual strolls, no unplanned escapes. The view out the window, if windows exist at all, will rarely change. A static landscape of dust and rock under a pink, thinned-out sky. Monotony, in this context, is not a minor inconvenience. It is a continuous psychological pressure. On Earth, Variety is constant and invisible. Different weather, new faces, a change in the smell of the air after rain. Birds, traffic, rustling leaves, distant music. Mars offers none of this naturally. Same walls, same corridors, same handful of voices. The soundtrack of existence becomes the hum of air recyclers and the soft click of machinery. In such an environment, the mind may begin to reach inward for stimulation. Dreams grow vivid. Small events, like a scheduled movie night or the rare arrival of a data bundle from Earth, take on outsized emotional weight. A delayed email can feel like a personal loss. A glitch in entertainment systems can feel like a minor catastrophe. The habitat may keep the body alive, but it asks the brain to live in a world where every sensory input is rationed. Even time itself will feel slightly off. A day on Mars, what mission planners call a sol, is about 24.6 hours long, just 40 minutes more than an Earth day. It sounds trivial, but our circadian rhythms are sculpted by millions of years of adaptation to a 24-hour cycle. Light, hormones, temperature, alertness, all follow this deep internal script. In early experiments, humans trying to live on a Martian schedule on Earth found their sleep drifting, slipping out of sync with local day and night. On Mars, this mismatch becomes the norm. Shift work, light therapy, and carefully timed routines will help, but the body will still be asked to dance slightly off-beat, day after day, year after year. Sleep disturbances, mood swings, and cognitive lapses are not just possibilities. They are patterns we may need to anticipate and manage constantly. Then there is the view of home. Astronauts orbiting Earth often describe the overview effect, a sudden, overwhelming sense of unity and awe when they see the entire planet in a single glance. Borders disappear. Conflicts seem small. Earth glows as a living, vibrant sphere. On Mars, Earth will be no majestic blue globe filling the window. It will be a star. A bright one, yes, but still just a point of light among countless others. The overview effect may experience its mirror image, a reverse revelation where instead of feeling connected to everyone, you feel the full weight of separation from them. Imagine stepping outside in a pressurized suit, looking up at a dim sky veiled with dust, and knowing that one of those tiny points of light is everything. Every ocean, every forest, every memory you have ever made. Home becomes not just distant, but almost abstract, a concept more than a place. For some, this may inspire a profound sense of purpose, a feeling of stewardship and responsibility toward both worlds. For others, it might trigger a deep, aching loneliness, a sense of exile written across the sky. Inside the habitat, the social universe condenses to a small group. Group dynamics in extreme isolation have been studied on submarines, polar stations, and simulated missions. Patterns emerge. Leadership styles become critical. Minor personality differences can snowball. Conflicts rarely explode dramatically. Instead, they erode slowly, like stress fractures in a hull. People withdraw. Cliques form. One person's coping mechanism, silence, humour, meticulous tidiness, may grate on another's nerves. On Mars, there is no option to go home early or transfer to another department. Every disagreement is a closed loop. Crews will need tools not just for fighting fires and repairing airlocks, but for repairing trust. Structured communication, shared rituals, transparent decision-making all become as essential as oxygen. The survival of the mission will depend as much on emotional resilience as on engineering. And beyond all of this lies something quieter, but just as potent: sensory deprivation. Mars is a world of limited textures. the crunch of regolith under boots, the dull thud of tools hitting rock, the thin, filtered light of a distant sun. The habitat will protect, but it will also filter, mute, and simplify reality. There is no forest to walk in, no ocean waves, no cities glowing at night, no sudden scent of flowers in spring. For months or years, the human sensorium will be fed mostly by artificial substitutes, screens, speakers, VR experiences, and printed images of a world that now exists only as memory. We don't yet know what happens to the human psyche when entire categories of sensation are removed for years at a time. We can guess, we can simulate, but the full answer waits on the surface of Mars. The real danger, then, is not just that Mars is hostile to our bodies. It is that Mars quietly asks our minds to become something new, something adapted to isolation, delay, confinement, and cosmic distance. Some will find in that transformation a kind of transcendence, a new way of seeing humanity and our place in the universe. Others may find a struggle that leaves invisible scars. The red planet will not just test our machines, it will test the stories we tell ourselves about who we are, what home means, and how far the human spirit can stretch before it begins to fray. We often imagine Mars as almost like Earth, a sky, a horizon, a place where dust settles on the ground instead of drifting in endless freefall. But beneath that familiar stage lies a fundamental difference that reshapes everything about being human. On Mars, gravity is not a comforting constant. It is a missing ingredient. Mars pulls with only 38% of Earth's gravity. A human who weighs 180 pounds on Earth would feel like they weighed just 68 on Mars. At first, that sounds like a superpower. You could leap higher, carry more, move with ease. But biology is written in the language of forces. Our bones, our hearts, our inner ears, even our developing embryos have been sculpted by 4.5 billion years under one unchanging pull. 1G. Take that away, and you are not just changing how we move. You are rewriting what it means to be human. We already have a glimpse of what happens when gravity fades from astronauts on the International Space Station. In the near-zero gravity of orbit, their bodies begin to forget Earth. Bones, no longer stressed by weight, start to dissolve. Calcium leaks into the bloodstream. Even with intense exercise, 2 hours a day of running, cycling, and weight training, astronauts can lose around 1 to 2% of their bone density per month in the most vulnerable areas like the hips and spine. That's osteoporosis, accelerated to science fiction speed. Now imagine Mars, not the complete absence of gravity, but a strange in-between state. Too weak to fully support Earth-adapted bodies, too strong to trigger the emergency countermeasures we see in orbit. A place where you don't float, but you also never really stand the way you do on Earth. Some scientists suspect that bone loss in 0G might actually overestimate what happens on Mars. Others warn of a more unsettling possibility, that partial gravity is its own unique stressor, a limbo where degradation is slower but unrelenting, creeping over years instead of months, a rate of loss just low enough to be survivable in the short term, and just high enough to be catastrophic over a lifetime. Bones grow and strengthen when they are loaded, that is, when they are forced to resist weight. On Mars, every step, every jump, every lift is reduced to 38% of the mechanical signal your skeleton has known for your entire life. For a mission of a few years, this might mean severe but manageable changes. But for a generation born and raised there, you have to ask a different question. What does a Martian skeleton look like? Muscle follows the same quiet rule. Without constant resistance, it fades. In orbit, astronauts' muscles can atrophy by nearly 20% in just a few weeks without exercise. The heart, no longer pushing against a full 1G column of blood, begins to weaken as well. When those astronauts return to Earth, many struggle to stand, their blood pressure collapsing when they try to walk. Their bodies have gently recalibrated for a world that doesn't pull as hard. Mars offers just enough gravity to walk, to run, perhaps even to convince yourself that everything is fine. But your heart will be pumping against only a fraction of the pressure it evolved for. Your leg muscles will never have to fight as hard to lift you. Your core will never truly learn what it means to hold you upright under 1G again. Cardiovascular deconditioning on Mars may unfold like a slow story, subtle fatigue climbing hills in early years, more frequent dizziness when standing, a gradually shrinking margin of safety when emergencies strike. Then, one day, a brutal realization. You are strong enough for Mars, but not for home. That is the hidden line in the Martian sand, the point of no return. A threshold beyond which the body has become so adapted to 0.38 G that returning to Earth's gravity would not just be uncomfortable, it might be impossible without years of rehabilitation or even lethal. Imagine a colonist in their 50s, born on Mars, whose bones are thinner, whose heart has never known 1G, whose muscles were never pushed to Earth levels. For them, stepping onto Earth could feel like being crushed. Their spine, joints, and cardiovascular system would all be forced into a regime for which they have no developmental history. Earth, the cradle of humanity, becomes an alien world. And this adaptation does not start in adulthood. It begins with the first breath, or perhaps even earlier. Pregnancy is one of the most delicate collaborations between gravity and biology. On Earth, a fetus develops in a fluid world, but the mother does not. Her blood, her organs, her posture, her circulation, everything is constantly regulated against 1G. The developing baby's bones, muscles, and inner ear all form in this context. Shift that entire process to 0.38 G, and we are no longer in the realm of small adjustments. We are in entirely unexplored territory. How does partial gravity shape a growing skeleton? Does the spine lengthen differently? Do joints form less robustly? Does the heart, learning how hard it needs to pump before birth, set a lifelong baseline for a lower gravity world? The inner ear may be one of the most sensitive pieces of this puzzle. Inside your skull, tiny structures filled with fluid and hair cells tell your brain which way is up. These sensors calibrate in early life to one thing: Earth gravity. It is the background constant that teaches you balance, coordination, and spatial awareness. In orbit, astronauts' vestibular systems are thrown into chaos. They feel disoriented, nauseated, their brains struggling to reconcile what the eyes see with what the inner ear feels. Essentially nothing. Over weeks, the brain reins in this confusion, building a new sense of down, based more on visual cues and less on gravity. Children born and raised on Mars would never know Earth's version of balance. Their brains would wire themselves around 0.38 G as the only reality. Place that child on Earth, decades later, and their inner ear would speak a language their brain never fully learned. Walking might feel like navigating the deck of a ship in a violent storm that never ends. The deeper implication is unsettling but fascinating. Mars might not just change individual humans. It could, over generations, begin to sculpt a new branch of humanity altogether. Lighter skeletons, different body proportions, hearts tuned for lower pressures, inner ears calibrated to a gentler pull. Even at the genetic level, natural selection may start to favor traits that thrive in 0.38 G, stronger bone metabolism, altered muscle fiber distribution, new cardiovascular strategies, traits that are not better or worse, but specifically Martian. Given enough time, going home might no longer mean stepping onto Earth at all. It might mean staying under a salmon-coloured sky on a planet that has quietly claimed your body as its own. The gravity problem on Mars is not simply that there is less of it. The deeper issue is that gravity is not optional, it is an architect. It has drawn the blueprints of our biology in lines of force and weight. Reducing it to 38% does not just make things lighter, it makes everything different. In the silence of the Martian night, under a sky pricked with cold, distant stars, a colony might one day look up at Earth as a bright, wandering point of light. A place their ancestors came from. A world with too much gravity. A world that in a very real physical sense, they may never be able to stand upon again. We have spoken of dust, radiation, and thin air as if Mars were a barren machine, a hostile but predictable environment. But there is a deeper uncertainty lingering beneath the frozen soil and rusted rocks. It is the question that has haunted every mission, every lander, every rover wheel that has ever etched a trail into Martian regolith. What if Mars isn't truly dead? For decades, we have treated Mars as a world long past its prime. Dry riverbeds, fossilized deltas, ancient lakes, a planet whose golden age of habitability ended billions of years ago. Yet, in the shadows of craters and buried beneath layers of dust, evidence whispers a different possibility. A planet not alive in the way Earth is alive, but perhaps still harbouring embers. Tiny pockets of persistence, microbes clinging to existence in places where sunlight never reaches. Beneath the polar ice caps, radar instruments have hinted at something extraordinary. Subsurface reflections consistent with liquid water, trapped under layers of ice and dust, warmed just enough by the slow decay of radioactive elements and the pressure of overlying material. Not lakes as we know them, not clear blue pools, but briny, hypersaline reservoirs, water so salty it refuses to freeze, even in the brutal Martian cold. Elsewhere, seasonal streaks on crater walls have tantalized scientists. Dark, narrow flows that appear in the warmer months and fade when temperatures drop. Are they the result of flowing brines seeping to the surface? Or are they simply dry granular avalanches playing tricks on our instruments? The debate continues, but the implications are profound. Where there is liquid water, even briefly, there may be niches where life could endure. If life ever arose on Mars, it would not need to be lush or visible. It could be microbial, slow and hidden, surviving in pockets of subterranean ice, within porous rocks, or clinging to the undersides of salt crystals. Life measured not by beating hearts, but by biochemical whispers. And if such life exists, our presence becomes something more than exploration. It becomes intrusion. This is why, long before talk of colonies and cities under domes, a quieter discipline emerged: planetary protection, an invisible layer of caution wrapped around every spacecraft we send. Robots destined for potentially habitable regions of Mars are baked, sterilized, and assembled in clean rooms where even a fallen eyelash is a concern. Not because Mars will infect us, but because we might infect Mars first. This is called forward contamination, the risk that hardy Earth microbes, clinging to metal bolts, wedged in cracks, hiding in insulation, could hitch a ride to Mars and find a niche to survive. If terrestrial bacteria colonize a Martian aquifer or endure just long enough in a brine-soaked crevice, we may never know if any future life we discover is truly Martian, or just our own biology reflected back at us. But there is another direction, one that lives in the background of science fiction, but is taken very seriously by the people who write real mission protocols. Backward contamination. Imagine a core sample returned from beneath the Martian surface, a cylinder of ancient ice, salts, and rock, sealed in titanium, carried carefully across the void, then lowering through Earth's atmosphere in a fireball of plasma. It lands in the desert, is whisked into a secure facility, and opened only within layers of containment more stringent than any hospital ward on Earth. Why such caution, if Mars may well be sterile? Because history has taught us a humbling lesson. Novel biology can be devastating. When Europeans arrived in the Americas, they carried with them microbes to which they had long been exposed. Smallpox, measles, influenza. To indigenous populations without prior exposure, these invisible invaders were catastrophic, scything through communities and rewriting human history within a few generations. A small shift in biology, a new pathogen entering an unprepared immune landscape, and the result was a pandemic. Now stretch that gap not across continents, but across planets. Not merely different populations of the same species, but possibly entirely separate branches of life, divided not by culture or geography, but by 4 billion years of evolutionary isolation. This is why the phrase unknown biological threat is not melodrama. It is a recognition of our ignorance. Yet some scientists suggest an even stranger possibility. What if Martian life is not just unfamiliar, but fundamentally different at the molecular level? On Earth, all known life is built from the same toolkit: DNA or RNA, right-handed sugars, left-handed amino acids, water-based chemistry. It is a single family, however diverse, sharing a common ancestral blueprint. But on Mars, if life began independently, it may have taken another path. This is the mirror life hypothesis. Life that uses the opposite-handedness in its molecules. Proteins that twist the other way. Genetic material based on alternative structures. Cells whose membranes and metabolism would be, from Earth's perspective, chemically alien. Such life might not infect us in the traditional sense. Our enzymes might not recognize its molecules. Our cells might not provide a hospitable environment. Its proteins might pass through our systems like glass beads in a river, strange but inert. And yet, that very incompatibility raises other, subtler risks. Could such organisms interfere with our closed life support systems, corrode materials, clog filters, consume vital resources in unexpected ways? Could they, in a Martian habitat, outcompete Earth microbes that we rely on for recycling air, water, and waste? Threat on Mars doesn't have to mean disease. It can be any biological process that undermines our fragile foothold. The contamination scenarios run both directions and multiply with each mission. A human crew steps out onto Martian soil. Microscopic life, if it exists, is kicked up by boots, drawn into airlocks, trapped in suits, brought into growing modules. A sample of regolith is heated for analysis in a small oven. If dormant Martian spores awaken in the warm, humid interiors of our habitats, would we know what we were looking at? Would standard decontamination work? Or would we be guessing in real time 140 million miles from a proper lab? Conversely, a return ship lifts off from Mars with cargo holds full of rocks and ice cores. Some microbial hitchhiker, Martian or accidentally terrestrial but altered by Martian conditions, rides along. Planetary protection demands that such material be quarantined upon arrival at Earth, studied with layers of redundancy, and never casually released into the open environment. Our challenge is to remain cautious without being paralyzed, curious without being reckless. We have already glimpsed how ambiguous this frontier can be. In 1984, in the Allan Hills region of Antarctica, a meteorite was found buried in the ice. Designated ALH 84001, its chemistry revealed that it did not originate on Earth, but had been blasted off Mars by a long-ago impact and wandered through space for millions of years before falling onto our polar cap. In 1996, a team announced that within this ancient Martian rock were structures and chemical signatures that might be evidence of fossilized life. Under microscopes, elongated shapes appeared, reminiscent of bacteria. Tiny carbonate globules seemed to hold organic molecules. Suddenly, the world was confronted not with a telescope image or radar profile, but with something far more intimate, a fragment of another planet that might have once harbored living things. Debate erupted. Were these true fossils or artifacts of mineral processes? Could such tiny structures be produced non-biologically? Decades of research followed. The consensus gradually shifted away from a biological interpretation, but the meteorite left us with something more important than a definitive answer. It taught us how difficult it is to recognize life when it does not come with a familiar label, how eager we are to find ourselves in alien patterns, and how necessary skepticism is when the evidence sits at the edge of our instrument's capabilities. Allan Hills 84001 remains a lesson in humility. Not proof that Mars was alive, but a reminder that the line between unusual geology and ancient biology is thin, especially when separated by time, distance, and imagination. As we contemplate human footprints in Martian dust, unknown biological threats are not just monsters in the red fog. They are questions about our own vulnerability, about the fragility of ecosystems, about how we define and detect life when it may not look like anything we've ever seen. Mars may be sterile. It may be a world of silence, where the only chemistry is rust, salt, and frozen air. Or it may be quietly inhabited at the microbial level, its last surviving biosphere hidden from our rover's cameras. Until we know, every plan to settle, to drill, to return samples must balance ambition with restraint. On a planet where everything already seems intent on killing us, cold, radiation, dust, thin air, there might be one more layer we cannot see. Not an army of Martian invaders, but a deeper challenge. How do we live on another world without erasing whatever might already be living there? On Mars, survival is not a state. It is a balance. A constant trembling equation between what you have and what you dare to use. Every sip of water, every breath of air, every watt of power is not just consumed, it is wagered. On Earth, we are surrounded by abundance disguised as background noise. Air presses against our skin with invisible generosity. Rain falls from the sky without asking permission. Soil quietly turns sunlight into forests, crops, and oxygen. We live inside an ecosystem where excess is normal and waste is an afterthought. Mars does not offer this illusion. Here, everything that keeps you alive must be pulled, forced, or carved out of a hostile environment. You are not a resident. You are an ongoing engineering project. Beneath the rusty dust and ancient riverbeds lies one of Mars's greatest promises: water ice. Orbiters have mapped bright patches near the poles. Radar hints at buried glaciers at mid-latitudes just beneath the surface. It is easy to imagine a future where colonists simply mine the ice and melt themselves oceans of drinking water. But the reality is more fragile. Much of Mars's ice is trapped in permafrost, mixed with soil and rock like cement. To reach it, you must dig through abrasive dust that clogs machinery, chews through gears, and coats everything in a fine, electrostatically charged film. Extracting ice is not a gentle scoop, it is a mechanical siege. Once the ice is in your habitat, it must be melted and purified. Martian ice is not clear mountain spring water. It may be laced with perchlorates, those same toxic salts that interfere with thyroid function and damage human tissue. The water that emerges from the ice must be filtered, sterilized, tested. Every litre is a small engineering victory, and the challenge is not just how much water you can extract, but how quickly. If your crew consumes water faster than your systems can produce it, your reserves begin to fall. One broken drill, one stuck robotic arm, one dust storm that forces you to power down equipment. The line between enough and not enough can be just a few days wide. Water, however, is only one variable in this delicate equation. Another is energy, the currency that keeps every subsystem alive. On the surface of Mars, sunlight is a distant memory of what it is on Earth. At best, solar panels receive less than half the intensity of sunlight we do. Every panel must work harder, spread wider, and be kept cleaner. But Mars is a dusty world. Tiny particles settle on glass surfaces, slowly smothering their efficiency. Robotic wipers and human crews must constantly clean them, using time, energy, and sometimes risking exposure to the elements. Then there are the dust storms, planet-wide veils of red that can dim the sun for weeks or even months. We have seen this before. NASA's Opportunity rover, powered by solar panels, slowly fell silent as the light faded and its batteries starved. On Mars, a similar fate awaits any human outpost that relies too heavily on the sun. Energy here is not just produced, it is gambled against the weather of an alien world. This is why nuclear power is often imagined as the backbone of a Martian settlement. Compact fission reactors can provide steady energy day and night, immune to dust storms and seasons. But nuclear reactors are complex, heavy, and politically sensitive. They must be launched from Earth, assembled, shielded, and maintained in an environment where spare parts are scarce and radiation is already a concern. A crack in a cooling loop, a malfunction in control systems. These are not quick fixes when resupply is millions of miles away. Energy is not a luxury on Mars. It is the blood flow of the colony. When power falters, everything else becomes negotiation. Do we heat the habitat or the greenhouse? Do we run the water extractor or the oxygen generator? On a planet where nothing is free, even decisions become a form of resource. Food, too, must be manufactured, not harvested. We often picture domed greenhouses under a pink sky, sunlight streaming through as rows of crops sway gently in Martian winds. But outside that dome, the soil itself is quietly hostile. Martian regolith is sharp, chemically reactive, and contaminated with perchlorates. It is more akin to crushed, toxic rock than to fertile earth. Before it can cradle a seed, Martian soil must be washed, treated, or even entirely bypassed. Instead of planting in the ground, colonists may rely on hydroponics and aeroponics, plants grown in nutrient-rich water or mist, their roots suspended in controlled environments. Every leaf, every sprout, becomes a unit in a careful biological calculation. Light in, water in, nutrients in, calories out. But even plants have their demands. They need stable light, stable temperatures, stable water. They need trace nutrients that may not exist on Mars in usable forms. And they need time. If a crop fails due to fungus, contamination, or a power loss that freezes water lines, there is no supermarket to bridge the gap. A failed harvest on Earth is an economic problem. On Mars, it is a countdown. The air itself must be manufactured as well. Mars offers a thin blanket of carbon dioxide, an atmosphere too sparse to breathe, yet dense enough to be useful. With machines like MOXIE, the experimental device tested by the Perseverance rover, we know it is possible to split that CO2 into oxygen and carbon monoxide. The chemistry works, the concept is sound, but scaling this from experiment to lifeline is another matter. Oxygen generation requires high temperatures, robust materials, and relentless power. The process is not perfectly efficient. Filters clog, components degrade, and the oxygen you painstakingly pull from the air must be stored, compressed, and circulated through habitats and suits. Every breath depends on pumps, valves, and seals that must work without fail. And then there is the calendar. Mars is not just distant, it is rhythmically distant. The orbits of Earth and Mars create a logistical pattern that cannot be negotiated. Roughly every 26 months, the planets align in such a way that the journey between them is relatively fast and fuel efficient. In practice, planning, windows, and trajectories turn this into something closer to a 22 to 26-month supply rhythm. Miss a launch window and your cargo, food, spare parts, replacement electronics will not simply arrive late. It may arrive years late. This 22-month problem turns every crate, every tank, every bolt into something more precious than it appears. A broken pump is not just a malfunction. It is a question. Do you have a spare? If not, can you repair it? Or will you have to redesign your life support system around its absence? To bridge these gaps, we imagine manufacturing on Mars, 3D printers quietly turning digital files into tools, brackets, and replacement parts. It is a comforting vision. Factories in miniature, conjuring objects from powdered regolith and metal feedstock. But 3D printing is not magic. Printers themselves require maintenance, calibration, spare nozzles, and specialized raw materials. Printing a simple plastic clip is easy. Printing a high-precision pump impeller, a pressure-rated valve, or a radiation-hardened circuit board is another world of complexity. Many things we casually replace on Earth are the end result of global supply chains, clean rooms, and specialized industry. On Mars, those chains terminate in a single fragile habitat. This is where the true danger of resource scarcity emerges. The cascade. Imagine a dust storm settles over your outpost, turning day into a dim twilight. Solar output drops. To conserve power, you throttle down non-essential systems. The greenhouses grow a little cooler. Lights dim. Plant growth slows. You rely more heavily on stored food. Meanwhile, the drop in power forces you to cycle your water extraction system less frequently. Reserves begin to dip. Showers become shorter, then rare. Air humidifiers reclaim every molecule of moisture they can, but it is not quite enough. Filters in your air recyclers dry out faster, wear out quicker. You go to replace a filter module, only to discover the spare was used months ago during a minor leak incident. The next scheduled shipment from Earth is still a year away. You could try to 3D print a component, but the printer has been limping ever since a previous power surge. Its replacement circuit board is on that same delayed shipment. And so one storm, one dip in power, begins to echo through water, food, and air. The safety margins shrink. Systems that were once robust become brittle. Life support does not fail dramatically. It erodes, one compromise at a time. On Earth, redundancy is a design preference. On Mars, it is a survival philosophy. The planet is not simply empty, it is unforgivingly specific. You must arrive not just with machines, but with enough knowledge, foresight, and humility to understand that every resource is a thread. Pull one too hard, and the entire web can begin to unravel. Walking this Martian tightrope means accepting a reality where abundance is an illusion and sufficiency is the highest luxury. It is a world where survival depends not on what Mars gives you, but on how delicately you can stretch what little it allows. By the time you step outside on Mars, the danger is no longer an abstract idea. It's the air that isn't there, the ground that grinds your tools into dust, the sky that looks calm but hides storms that whisper in voltages instead of sound. Mars is not simply uncomfortable, it is a planet where the environment itself is constantly, patiently, trying to erase you. On Earth, we talk about a cold night or a hot day. On Mars, those two things can be the same day. Near the equator, a midday sun can warm the surface to around 70 degrees Fahrenheit, a temperature that feels almost familiar. But as that thin atmosphere leaks its heat back into space, the warmth vanishes with brutal efficiency. Night brings a plunge toward negative 140 degrees. A swing of more than 200 degrees in a single Martian day. Metal contracts, plastics stiffen, electronics cycle from soft warmth to biting cold over and over again. Every joint, every cable, every seal is forced to breathe with the planet's violent temperature rhythm. What feels like one sunrise to a human is a full mechanical lifetime to the materials that keep them alive. Inside a habitat, heaters hum, systems compensate, walls insulate. But step outside in a suit, and you are one fabric shell away from a world that doesn't just ignore human biology, it actively tears at the engineering that protects it. A tiny flaw in thermal control becomes more than a maintenance issue. It becomes a countdown. Temperature doesn't just threaten machinery, it changes the very behavior of one of the most familiar substances we know, water. On Earth, ice melts into liquid, liquid boils into vapor. On Mars, that simple story breaks. The pressure at the surface is so low that liquid water can rarely exist in a stable state at all. Ice exposed to the open air doesn't melt first, it jumps. Sublimation, the direct leap from solid ice to vapor, is not a minor detail here. It is the default. A droplet of liquid water spilled on the surface won't form a puddle that lingers. It flickers, flashes, and vanishes, stolen by the near vacuum, torn between freezing and boiling at the same time. For biological tissue, that same tug of war is deadly. Human cells depend on water held delicately inside flexible membranes. Expose that tissue to Martian conditions, say through a breach in a glove or a tear in a suit, and the water inside doesn't simply freeze gracefully. It races outward, trying to expand, trying to evaporate. Cell walls rupture, structures collapse, moisture is stripped away molecule by molecule. In a sense, Mars doesn't have to burn you or drown you. It can simply let your own internal water tear you apart on its way out. Even if you stay well sealed, the surface itself offers another quiet threat: chemistry. The soil of Mars is not just inert dust. It is reactive, oxidizing, and strangely aggressive toward the very molecules we associate with life. Organic compounds that should linger in the ground are often missing or severely degraded. Instruments that expect to find simple carbon-based molecules discover instead the scars of destructive reactions. One of the culprits: oxidizing agents in the regolith and atmosphere, compounds that can rip electrons away from molecules, breaking them into simpler, lifeless fragments. Think of them as chemical sandblasters, constantly scouring away any delicate carbon structures that might once have existed at the surface. For future astronauts, this means that the Martian ground is not just dirty, it is chemically hostile. Dust brought into a habitat could slowly corrode equipment, degrade seals, and complicate efforts to study possible biosignatures. Experiments designed to detect life must first dodge the planet's talent for erasing its own history. And sometimes the surface does more than erase, it charges. On Earth, we know static electricity as a small annoyance, cloth clinging in the dryer, a spark when you touch a doorknob. On Mars, static may be a planetary-scale phenomenon, woven into the fabric of its dust storms. As particles of dust and sand collide and rub against each other in Mars' thin, dry air, they can build up impressive electric charges. Some laboratory experiments and rover measurements hint at the possibility of powerful electric fields within dust devils and storms. Fields strong enough to create discharges, alter chemistry, or interfere with delicate electronics. Imagine walking across a landscape where every drifting grain under your boots is a tiny capacitor, where the wind doesn't just move dust, it charges it, lifts it, sorts it by electrical sign. Where a dust devil crossing the horizon is not just a swirling column of soil, but a moving electrical machine. For habitats, rovers, and suits, this static environment could translate into unexpected hazards. Electrostatic discharges that damage sensors, confuse communication electronics, or accelerate corrosion. Even fine dust clinging stubbornly to visors and solar panels might be held there in part by unseen electric forces. Then there is the dust itself, not just charged, not just chemically reactive, but physically abrasive. Martian regolith is not like beach sand, worn smooth by relentless waves. It is sharp, angular, the crushed remains of volcanic rock and impact-shattered crust. Without the constant tumbling in liquid water that rounds Earth's grains, Martian dust remains more like powdered glass. When this abrasive material swirls in the wind, it becomes a constant grinding agent. It seeps into hinges, seals, and bearings. It scratches visors, dulls solar panels, and gnaws at flexible joints in spacesuits. Every step outside is a negotiation with a world that is trying to sandpaper away the tools that let you walk upon it. During the Apollo missions, lunar dust taught us a smaller version of this lesson. It clung to everything, irritated lungs, and wore down seals in just a few days of exposure. Mars offers an entire planet built on a similar principle, but with weather dynamic enough to move that dust across continents. Those winds are often gentle, but they are not always quiet. Martian weather, to our eyes, looks subdued. Thin clouds, a faded sky, soft-edged horizons. Yet within that subtle atmosphere are patterns we are only beginning to map. Local dust devils tower kilometers high, carving temporary dark tracks across the surface. Seasonal storms can arise in one hemisphere and, on rare occasions, grow until they swallow nearly the entire planet in a global haze. Winds may be weaker than Earth's hurricane gales in terms of sheer force, but their reach is vast. A storm that can dim the sun for weeks is not just an inconvenience. It is a direct threat to solar power, navigation, and the psychological resilience of anyone watching day turn to a long, dust-choked twilight. We have seen storms strip the skies so thoroughly that solar-powered rovers drifted slowly into silence, starved of energy under a dim red shroud. Somewhere beneath that same kind of storm, a human outpost would depend on battery reserves, backup reactors, and careful planning to outlast a sky that has forgotten how to be transparent. And still, the full catalogue of Martian weather remains incomplete. We are discovering new patterns, unexpected cloud layers, sudden pressure fronts, temperature inversions that trap cold where there should be warmth. Each mission adds pieces to a puzzle. How dust, temperature, chemistry, and electricity all dance together above this barren world. On Mars, danger does not announce itself with roaring oceans or crashing thunderstorms. It arrives in subtler forms. A slow drift in temperature that stresses a seal. A whisper of static in a dust-filled breeze. A chemical reaction that quietly dissolves the evidence you hope to study. Here, survival is not just about escaping one threat. It is about living inside a web of overlapping hostilities, where every part of the environment, air, soil, temperature, chemistry, is leaning gently but persistently toward your failure. To walk on Mars is to inhabit that tension. To build there is to accept that your habitat, your suit, your own body are not fixed things, but ongoing negotiations with a planet that never truly makes peace with your presence. On Mars, the first real crisis may not come from a dust storm, a habitat breach, or a failing life support system. It may begin with something deceptively ordinary. A twisted ankle on a rocky slope, a kidney stone in the middle of a work shift, a simple appendicitis that, on Earth, would be a routine surgery and a same-week discharge. On Earth, these are inconveniences. On Mars, they are turning points. The nearest fully equipped hospital is not across town, or even across an ocean. It is a moving blue star in the sky, separated by up to 140 million miles of vacuum and delay. There is no helicopter evacuation, no emergency room, no second opinion down the hall. There is only what you brought, and what you can improvise. Imagine a crew member slipping while unloading regolith bags, landing badly on an outstretched arm. On Earth, X-ray, plaster cast, pain meds, maybe minor surgery. On Mars, the arm swells in a habitat where every cubic centimetre of atmosphere is counted, where water for ice packs is part of a tightly balanced life support system, and where even a small infection can turn into a mission-threatening crisis. The complications start immediately. Reduced gravity changes how blood pools and how fluids move in tissue. Swelling behaves differently. Bruising spreads in unfamiliar patterns. Bones already weakened by months of 38% gravity may fracture more easily and heal more slowly. An injury that would be a brief setback on Earth becomes a question with no easy answer. Can this person ever return to full duty? And what happens if they cannot? Now extend this to more serious emergencies. On Earth, a heart attack is met with defibrillators, cardiac cath labs, teams of specialists. On Mars, the defibrillator must share power with the air recyclers. The cardiac team might be a single doctor or no doctor at all, supported by crew with weeks of emergency medical training and a manual written for a world where gravity is constant and supplies are infinite. Stroke, sepsis, anaphylactic shock, childbirth complications, severe burns from an equipment failure. Each of these is already a race against time on Earth. On Mars, that race is run on a tilted track. Surgery, the ultimate last resort of medicine, becomes something stranger still. Operating rooms on Earth are carefully controlled worlds, bright, sterile, filled with instruments and machines that hum quietly under full gravity. On Mars, any operating room must coexist with the habitat's oxygen lines, its temperature controls, its fragile seals that keep the planet outside where it belongs. Under reduced gravity, even the fundamentals of surgery change. Blood does not obediently flow downward, and pull away from the surgical field. It forms rounded droplets, clinging to tools, floating if not carefully contained, threatening to contaminate instruments, air filters, and electronics. Smoke from cauterization hangs in the air rather than drifting up and away. Sterility, already hard to maintain in a dusty, closed environment, becomes a constant negotiation. Every suture, every incision, every movement of a scalpel must account for a world where fluids misbehave and where even a minor infection could spread through a crew with limited antibiotics and no backup hospital. And those antibiotics, they face their own silent enemy: time. Medications are designed to sit on shelves under relatively stable conditions: normal gravity, predictable temperatures, protective packaging. On Mars, medicines endure months of radiation on the journey out, subtle but relentless vibrations, storage in cramped, multi-purpose modules where temperature control is good but not perfect. Over years, some drugs slowly lose potency. Others may break down into compounds that haven't been fully tested under deep space conditions. Pharmacies on Earth restock weekly. Pharmacies on Mars restock every 26 months. If the launch windows are met, if nothing fails en route, if political and economic tides on Earth remain steady. A missing crate is not a paperwork problem. It is a hole in the future medical capability of an entire colony. The same scarcity shapes diagnostic tools. On Earth, a mysterious pain can trigger a cascade of tests: CT, MRI, ultrasound, blood panels, specialist consultations. On Mars, diagnostic equipment must be small, rugged, power-efficient, and multi-purpose. There may be one compact ultrasound instead of a room full of imaging devices, a small lab capable of basic blood tests rather than a hospital-scale analyzer. When a crew member presents with subtle neurological symptoms, is it a microstroke, radiation-related damage, or sleep deprivation from months of disrupted circadian rhythms? Without advanced imaging, medicine on Mars becomes closer to the art it once was, listening, observing, inferring. Only now the stakes include the possibility of losing not just a patient, but a vital member of a tiny community. These limitations sharpen every ethical edge. On Earth, triage is painful but buffered by abundance of hospitals, of personnel, of backup. On Mars, there may be a single surgical kit, a finite supply of anesthesia, one ventilator that doubles as an emergency backup for the life support system. If two crew members are injured in a habitat accident, one with severe burns needing intensive care, another with internal bleeding requiring immediate surgery, who gets the ventilator? Who receives the last units of a critical drug? Do you risk using experimental techniques or untested protocols if they might save a life, or conserve resources for future emergencies? Triage becomes not just a medical choice, but a colony decision. Each person is not interchangeable human capital. They carry unique skills. The only agricultural specialist, the only propulsion engineer, the only physician. The calculation is brutal. Saving one life may save the colony, but letting someone die may break the fragile social fabric that holds the group together. Radiation weaves through all of this like a slow, invisible thread. Even at the best shielded sites, Martian settlers will accumulate more radiation dose than almost anyone on Earth. This affects wound healing, increases cancer risk, and may impair immune function. A broken bone might mend slowly or imperfectly. A simple skin tear could become a chronic, non-healing ulcer. Chemotherapy, should it ever be attempted on Mars, would be layered on top of an already stressed biology. And while the body absorbs radiation, the mind absorbs something else: isolation. Mental health on Mars is not a side topic. It is a central pillar of survival. Anxiety, depression, panic attacks, and episodes of psychosis are not hypothetical. They are statistically likely in long-duration, high-stress, confined environments. Conflicts between crew members, grief over losses on Earth, claustrophobia in sealed habitats, and the oppressive awareness that outside every thin wall is a world that will kill you in seconds. These are not cinematic embellishments. They are background conditions. Intervening in a mental health crisis 140 million miles from Earth is a challenge we have never truly faced. A crew member having suicidal thoughts or experiencing a break from reality cannot be quietly transferred to a dedicated facility. They remain with the same small group, in the same tight corridors, under the same relentless mission demands. Telepsychiatry with Earth-based professionals may help, but signals are delayed by up to 22 minutes, one way. Real-time conversation turns into staggered monologues. In the time it takes to ask a question and receive an answer, an entire situation can change. So Mars settlers will need to become not only technicians, engineers, and explorers, but also each other's counselors and guardians. They will have to decide, together, what to do if someone becomes a danger to themselves or to the mission. How do you restrain, isolate, or medicate a friend when there is nowhere else to send them and no one else to take your place? On Mars, a medical emergency is no longer a brief spike of terror followed by sirens and white coats and bustling hallways. It is a slow, unfolding test of preparation, improvisation, ethics, and endurance. Every bandage, every tablet, every scan carries the weight of distance. Every decision is made in the knowledge that help is not on the way. Living on Mars means accepting a new definition of vulnerability, not just to the planet, but to the limits of our own medicine. As our journey across the Martian landscape comes to an end, we look back at what we've crossed. Not valleys and canyons, but layers of invisible danger. Dust so fine it slips past filters and lungs. Radiation that etches itself silently into DNA. An atmosphere that is both too thin to shelter us and just thick enough to carry storms, poisons, and cold. Gravity that loosens bone and unravels muscle. A world where the ground itself may be laced with toxic perchlorates, and where even loneliness becomes a kind of weather, wearing at the mind day after day. Mars is not one problem. It is a tapestry of threats woven together, each strand tugging on the others. A torn suit in a dust storm is also a radiation emergency. A supply delay becomes a medical crisis. A psychological fracture in a habitat perched above a frozen desert is no longer just a bad day. On Mars, every system is connected, and every failure is amplified. Yet recognizing this does not mean turning back. Understanding Mars's dangers is not a reason to abandon it, but the only honest way to approach it. Every civilization that ever set sail across unknown oceans first learned to name its storms. All over Earth, researchers are already quietly rehearsing the Martian struggle. In desert labs, analog crews simulate isolation and confinement. In orbit, astronauts study how bodies bend under low gravity and slow atrophy. Engineers grind artificial regolith into filters, test habitats against abrasive dust, design magnetic shields and underground shelters against radiation. Chemists dissect perchlorates, searching for ways to neutralize them, or even turn them into oxygen and fuel. Psychologists map out what happens to the human mind when the horizon never changes. The question is not only how we will solve these problems, but when. Are we pacing ourselves with the reality of Mars, or sprinting towards it with more optimism than preparation. Between bold timelines and careful science, there is a tension that will define the first human footsteps on the red planet. Too fast, and Mars becomes a lesson in hubris. Too slow, and we risk letting fear write the final chapter for us. But humans have always lived at the edge of what is survivable. We learned to breathe thin air in mountains, to master ships on black oceans, to wire entire planets with thought. Adaptation is our oldest technology. Determination is our quiet fuel. Mars will not welcome us. It will test us. It will strip away illusions of easy colonization and replace them with hard questions of ethics, risk, and resilience. Yet somewhere in that harshness is the possibility of a new chapter for our species. Not a second Earth, but a mirror held up to the first, reminding us how rare a living world really is. If this journey through Mars's hidden dangers kept you company tonight, you can help this exploration continue. Tap like so the algorithm knows to send more science into your evenings. In the comments, let me know where you're listening from, city, country, or maybe just under the stars. And if you'd like to support the channel more directly, there's an optional YouTube membership available. It's never expected, but always appreciated. Subscribe if you'd like to return to these quiet voyages across planets, storms, and the deep red uncertainties that still wait for us in the dark. Mars may be more dangerous than we imagined, but so too is our capacity to understand, to endure, and to keep going anyway.